All right, so today we're going to talk about dynamic programming, which is a meta-algorithm or optimization technique that you can employ to solve certain problems and solve them faster. So dynamic programming is technically a combinatorial optimization technique using the principle of optimality, which is something that he defined and talked about a great deal in his books and his papers, and showed, by graphs and proofs that optimal solutions are made of optimal sub-solutions. And we're going to revisit that idea as we look at several different problems. But before we do that, let's look at a couple other definitions here. So in computer science, you know that a divide and conquer technique is often implemented with recursion, which takes a top-down approach. So dynamic programming we can think of as completely skipping the top-down recursive approach. Instead, it starts at the bottom. It starts with many sub-solutions, and it continues to compute all the sub-solutions until it reaches the final solution. So in some ways, dynamic programming is thought of the opposite of recursion, if you will. So not a top-down approach, but a bottom-up approach to solving a problem. So what is recursion first, before we look at some recursive solutions versus DP solutions? So recursion is a technique derived from a recurrence relation, right? An equation defined in terms of itself. So a classic example of that is the Fibonacci sequence. This existed in math before the first computers and before programming. And so it was very natural for mathematicians to use this type of solution to solve problems. But as though that's elegant and concise mathematically, we know over the decades that implementing a recursive solution often suffers from some inefficiencies, such as the most common one is excessive function call overhead. If you have a recursive solution, you have a very large recursive tree. It's making lots of function calls. Every call that it makes puts information on the call stack, a stack frame, if you will, for each function call. And that can eventually, if the recursive tree gets too large, that can actually blow your stack, right? So you can have a stack overflow exception. So that is often thought of as like the biggest complaint with recursion, but actually there's an even bigger inefficiency with it, which is the overlapping subproblem issue. Overlapping subproblems, or subproblems that occur multiple times when you're breaking a problem down. So let's look at computing the Fibonacci numbers recursively, right? So our recurrence relation is the same. Here is one implementation or solution that we could do. If we call Fibonacci of some number, let's say we want the 5th Fibonacci number, well, we have our base case, which matches our recurrence relation base cases here, and then we recurse otherwise, producing this recursive tree, right? So if we want the 5th Fibonacci number, well, that's going to be adding the 4th Fibonacci number plus the 3rd Fibonacci number, right? To get the 4th, we need the 3rd. The 2nd, to get the 3rd, we need the 2nd, 1st, and so forth and so on, right? So this is breaking down the problem, right? Top-down approach. We are computing all the subproblems. So not only do we have the excessive function call overhead, but a much bigger problem here is this. All of these subproblems have already been solved. When we get to this point and we need to compute the Fibonacci of 3, well, we've already computed that here. So why would, when we're recursing back, do that again? It turns out 9 of these subproblems are a waste. To get the Fibonacci number 5, we only actually needed to compute 6 unique subproblems. So obviously this is the real killer with a lot of recursive solutions. I mean, even if we look at Fibonacci of 20, which isn't even that large of a data set, that's generating 21,891 function calls, right? Only 21 of which are actually unique subproblems. So of course we're talking about dynamic programming. Let's look at a DP solution to computing the Fibonacci numbers. We have the same recurrence relation. To compute a Fibonacci number, you need the 2 previous, except we're not going to break this problem down recursively. Instead, we're going to build a table. So here's the code that you could look at, and we're going to build this table, right, of all of our subproblems to get to our final solution here. But to get, let's say, the Fibonacci number of 2, well, to get 5, we're going to have to compute all the way up. So to get 2, we need the 2 previous, right? So that is 2. To get 3, we need the 2 previous, so that is 3. To get 4, we need the 2 previous, that's 5. And to get 5, which is the actual solution we wanted, that's the 2 previous in the table, which is 8. So this is a very quick implementations, because you have no function call overhead, you have no overlapping subproblems, you're computing all the subproblems up to the final solution. And the only downside to this, for this solution, we had to store n+1 space. So if you wanted the 100th Fibonacci number, you have to store, for this solution, 101 integers or numbers or whatever you're using in your table here. So let's look at another problem, the change-making problem. So this is an interesting little problem. You've definitely encountered it before. And it says, so if I want to make change for some amount of money, given these denomination of coins, so for instance, this could be US currency, how many coins does it take to get change for that number, right? For that amount of change that I want to compute for. So we're computing not the coins themselves necessarily, but how many coins does it take? Well, for US currency, it would take 5 to reach this, right? And how did we get that? We were employing a greedy algorithm. Most of us, that's what we think of first. So to compute change for this amount of change, given this denomination, the best we can do is 5 with a greedy algorithm, right? If we had these denominations, so let's say our change machine did not have access to a 50-cent piece, it would compute the change like so. So let's consider an instance of this problem where you're trying to produce change for a certain number, let's say 6, but we only have denominations of 1, 3, and 4, which is admittedly a very weird denomination set, but it's certainly an instance of the problem that could exist, and you could reduce this problem to other types of problems that are very similar. Well, let's look at this. If we employ a greedy algorithm here, we would take a 4-cent piece, that would knock that down to 2. Then what are we left with? We can't use a 3-cent piece. We'd have to use 2 1-cent pieces. So the best we could do is 3 coins, right? A 4-cent piece, a 1-cent piece, and a 1-cent piece. That's 6. But we know if you look at it a little bit closer that the best we could really do is 2 3-cent pieces. That's 2 instead of 3 coins, right? So, but we can't get that with a greedy algorithm. Right? And you being the good computer scientist that you are, you're saying, well, is there a fast algorithm that can handle any denominations? And the answer is dynamic programming, because that is what we're talking about here. Dynamic programming solution to change making. We want to compute change for any amount n using the least number of coins. That's our goal. We want to handle any logical variation of denominations, right, as we've shown on the previous slide. And when I say logical, I mean you wouldn't have a currency that would have 5 different types of 1-cent piece. And we want to exploit this principle of optimality because we're using DP. Optimal solutions are composed of optimal sub-solutions. So let's break this down, a little bit more specifically so we can write a program. We have D, which is a table of our denominations. These are just our different coins, right? So where D0 is 1. So a 1-cent coin, this one is strictly greater than this is strictly greater than this. So this could be a 1-cent coin, a 3-cent coin, a 4-cent coin, etc. So this is a small list of just our types of coins. And then C is going to be our table of subsolutions. So like the Fibonacci problem, we're going to have a table of subsolutions that we're going to use to compute all the way up to the final solution. And here is our recurrence relation, which looks confusing. I'm going to read through it quickly, and then we're going to just jump to an example. At first, when people look at DP solution recurrence relations, they look pretty complex. So we're going to start our table out with C sub 0 is 0, because if you think about it, if you're making change for 0, well, that's 0 coins, right? So you don't need to do anything. That's done. That's our base case. Every other n beyond that, if we're making change for 1 or 5 or 6 or 67, we're taking the minimum of, so that a key that we're looking at multiple things, we're taking the minimum of looking previous in our table, so if this is C sub n minus something, and then what? Which ones? Well, D sub j, where j goes from 0 to n minus 1. So D sub j is going to be our different denominations. So n minus this denomination, n minus this denomination, and so forth. We're going to look at those previous subproblems, all right? And we're going to take the minimum of them. So to write this DP solution of the change-making problem, we have our problem definition from the previous slide. Here is our code, but before we explain the code, right, which is literally just an implementation of this recurrence relation here, before we explain that code, let's just jump into an instance of the problem. So here we're making change for 6, so n is 6. We're making change for 6, and this is our denominations here. But let's just jump in. We know we're going to compute all the way up to get how many coins are needed to make change for 6. But let's look at halfway through it. When making change for 3, we're looking at the best we did previously, right? But then adding one more coin. But which coin are we going to add? When making change with 3, if we look at, well, first of all, we wouldn't even consider coins of denomination 4. That wouldn't make sense, because if you're making change for 3, why look at a 4-cent coin? But we could be taking a 1-cent coin on top of what we did previously. So taking a 1-cent coin would move us back to 2. Well, what was the best we did with 2? It turns out we did 2 coins to get to this point. So 2 coins plus 1 new coin, that would give us 3. But is that the best we could do? What about if we chose a 3-cent coin? So if we chose a 3-cent coin to make change for 3, well, let's jump all the way back. What is the best that we did, minusing that 3-cent coins? What's the best we could have done before that? Well, you know, we had nothing before that. So we could take 1, so 0 coins plus 1. 1 3-cent coin could give us an answer of 1, right? So 1 coin, that is the best, that is the minimum of all of our, looking at all of our sub-solutions plus adding 1 coin, that is the best that we could possibly do, right, for 3, right? So to get 3, we were looking at this sub-solution and this sub-solution, right, to get the most optimal solution, which would be 1 3-cent coin. Let's go through the whole table real quick here. So this is our denominations. This is our sub-solutions all the way up to what we want to provide, change for 6, how many coins for 6, right? So to get 0, right, how do we make change for 0? That's simple, it's 0. How do we get change for 1? Well, we want to look at the minimum of considering all of our denominations here. We don't want to consider change for 3, a 3-cent coin or a 4-cent coin. That wouldn't make sense for change for 1. But we consider a 1-cent coin. So we look at our previous best, which is, you know, C sub 1 minus 1. So C sub 1 that we're on minus the 1-cent coin, right? What is our previous best? 0 plus 1 coin. Well, that's just 1. All right. 2, we're looking at our previous bests. We wouldn't consider a 3-cent coin or 4-cent coin. So our previous best, we're just looking at sub 2 minus our 1-cent coin. So our previous best is 1. So the best that we can do is that plus 1 here, right? So we are left with 2 coins to get change for 2, which is, you know, this is making sense given our denominations. Here is where it gets interesting. We start looking at all of our denominations here. So we're looking at if we take a 1-cent coin or a 3-cent coin or a 4-cent coin, what is the previous best that we could do? It's 0. 0 plus 1 is 1. So to get change for 4, we would have 1 4-cent piece. That makes sense. And then finally for 6, which is what we want to find out from the beginning, how many coins does it take with this denominations to get change for 6? Well, let's look at our previous subsolution, which is the most optimal, 1, right? And so 1 plus 1, so it is 2 coins, right? So we know now to make change for 6 that you need 2 coins, right? Which we kind of knew from the beginning. This is a simple problem instance. But you are a smart computer scientist and you're immediately thinking, okay, that's cool. I can get the number of coins, but which coins specifically? We know it's 2 3-cent coins from this simple problem, but which 2 coins? Let's compute that. It'd be nice if our algorithm could compute that. Well, our problem definition really didn't include that at first, but if you really want to know, it's possible because now we can use this table of sub-solutions to traverse backwards to figure out what we want. But we actually need some additional information. So this is where some additional memory comes into play. We would need another table, right? So I've called this table S for selection. It's arbitrary, but we need another table to say that when we chose our coin here to get to 6, what did we choose? Which denomination coin did we choose? Well, at the end here, if you look back at the previous slide, at the end here we chose a 3-cent coin. All right, so we chose a 3-cent coin. Well, I could use that to jump back to the previous solution, that we used to get this 3-cent coin. And from there, what did we choose to get to this point? Well, we actually chose a 3-cent coin as well to get to this point from here. So I could jump back again by 3, right? And we're actually done here. We've exhausted all our change. So it turns out this is our list of coins here, right? You could keep track of that. You need these two tables, but you could backtrack and then you could have which coins. So obviously this is a simple problem instance, but let's say you were giving change for 83 cents with this denomination set. You could use this technique to jump back and have your list of coins. So we've seen some performance gains potentially from using DP over, just straight recursion. And also DP can be used to solve some very complex problems or problems that we don't have better solutions for. But there are a couple of drawbacks, some which you've already detected, like it often requires more space. So again, the space-time trade-off. Potentially, it can solve sub-solutions that would have never been attempted with a recursive solution. In other words, there exist problems where recursive solutions would only have considered a subset of the problem, not all of the subproblems, especially if you're using optimization techniques like backtracking or forward checking. And the final note here is memoization, as we mentioned. Sometimes it's often worth, since these are, once you figure out how to do DP and the recursive solution, memoization is just as easy. So it's often beneficial to implement both and then just profile based on the different data sets or problem instances that you might encounter and see which one would be faster for you. But hopefully now you understand a little bit more about dynamic programming and how you could use that to solve certain problems, or at least understand algorithms that have DP solutions to them.